Alright, good evening. Sorry, so past midnight already. So, good day. Hope you are all doing well. So, as I've mentioned before, we're going to tackle a little of the triangle congruence, you little bit of recall or something. So, triangle congruence, we have so many terminologies that we have to dive into. We just lowered the audio. Alright, so as I was saying, so we have CPCTC. CPCTC, we've already encountered CPCTC, so the ones we use when we do the proving, right? So it means that congruent parts of congruent triangles are congruent. No? We also have CPCTE. So when these congruent parts of congruent triangles are congruent, then these congruent parts are also equal. So just change the congruent to equal. So meaning we can equate the two corresponding sides or angles to each other. So if for example, it will be represented by it will be represented by algebraic expressions, and you are asked to solve for the value of x or any variable that represents that is used in the representation. So continue. So in this case, we have the SSS congruence postulate. No, so if three sides of the one triangle are congruent to the corresponding sides of the other, then two triangles are congruent. So for example, this one ABC and DEF. So if you notice, there are markings right there that you can see. So that is an indication that these sides correspond to these sides. AB corresponds to DE and so on. So just to look at the marker, okay? So by triangle ABC is congruent to triangle DEF given the following corresponding sides by SSS postulate. So we have here an example. So statements LO is congruent to LE given, and then EV is congruent to VO or OV, right? And of course, LV there is the common side. So LV by itself is a reflexive property of equality. And then that means automatically you can say that the two triangles LEV and LOV are congruent to each other by SSS postulate, right? Okay, another. Let's just proceed to the other. I think there are three examples for this, so I'm just going to run through. So now we proceed to SAS, congruence postulate. So if two sides and the included angle of one triangle are congruent to the corresponding two sides and the included angle of another triangle, then the two triangles are congruent. So in illustration, if for example, ABC here, triangle ABC, if you notice, this side corresponds to this side, and then there's an included angle between these two sides. So is it necessary to have it like that? So actually, you can just it doesn't matter where the angle is located as long as the angle is in between the two sides. No? So if, for example, you say it's supposed to be like this here, and that, no, so and so on. That's still possible, no? That's still viable as long as it is drawn to the other side as well. But in this case, it looks like this, okay? So that one. So this side corresponds to this side, and this angle B corresponds to angle E, and then BC corresponds to EF. So, and by that, by SS, sorry, this is not the exact. Supposedly, this is AB to DE, angle B, angle E, and BC. This is SAS, huh? SAS. Okay, another error. So an included angle is the angle formed by two given sides. So always take note of that. Also, this one, if just an angle, it's not an included angle, okay, alone. So, for example, walang marker dyan, no? So, if they just take note that the angle should be in between two sides, no? So, an included angle is the angle formed by two given sides. Let's proceed to some examples. So, the included angle is the angle formed by the angle between two sides. In the diagram below, angle B is the included angle of side BA and BC, right? And angle A is the included angle of side EE and side EF. So in this case, sample, let's try to prove BA is congruent to BF, right? And angle A is congruent to angle F. So even if the illustration is like turned 180 degrees or flipped 180 degrees, 90 degrees, and so on. For as long as the marker is there, you should follow the markings, right? So if this marks for the congruence between the two angles, and these two angles are congruent, no? So if, for example, it's written here, then yeah, you have to really follow whatever the congruence states, no? So and so on. So AC is congruent to EF or FE, and then by SAS postulate, these two, triangle BAC is congruent to triangle BFE. SAS na. So proceed ko, run through lang. So now we have ASA, right? So if two angles on the included side of one triangle are congruent to the corresponding two angles and the included side of another triangle, then the two triangles are congruent. So this the congruence postulate before this one is opposite to this, right? Earlier it was included angle. This time it's in the included. There's an included side now. So there's two angles, and in between the two angles, nice side, right? So for example, if angle B is congruent to angle A, and side AB is congruent to side DE, which is the side. Angle A is congruent to angle D, then triangle ABC is congruent to triangle BF. Again, included side is the side whose endpoints are the vertices of two angles. So here, for example, yeah, anyway, this is just narrative. Side BA is the included side of angle B and then angle A. Side ED is the included side of angle E and angle D. So for example, let's try to prove that these two are congruent. Angle A is, what does angle A corresponds to? Angle O, right? Oh, sorry. Oh my God, that's supposed to be angle O, okay? Angle O, and for the side, AT is congruent to OG, right? Yes. And for the angle T is congruent to angle G. So if you notice this one, okay? And by ASA postulate, triangle CAT is congruent to triangle BOG. All right. So by ASA postulate. So and then some examples. Then we have the side angle congruence. Actually, sometimes they can be AAS or angle side. So two angles and a non-included side of one triangle are congruent to the corresponding two angles, and then non-included side of another triangle, then the two angles are congruent. Right. So for example, side angle side, or sorry, side angle. Okay. So BC corresponds to is congruent to EF for the side. Angle B is congruent to angle E, and angle A is congruent to angle D. Therefore, by triangle ABC is congruent to triangle DEF. So always take note that two angles first should come, or there should be consecutive angles, not well, somehow they should be consecutive. It will follow naman sa video. So please take note of that. Side angle. So coded side is the side whose endpoints are the vertices of two angles. This one was actually for the ASA. So, for example, prove that AC, given AC is congruent to BD and AC is parallel to BD, prove that triangle ACE is congruent to BDE. So we have the given, just write the given, angle C is congruent to angle D, right? And parallel and alternate interior angle postulate. So that's another terminology. And then we have the AEC. AEC is congruent to BED. Vertical angles are congruent. And ACE, triangle ACE is congruent to triangle BDE by SAA postulate. Congruence theorem. Okay? I think there's still, I think this would end. I'm just going to pause. All right. So as mentioned the other day, so I mentioned about giving examples on solving part for the application of the theorems, right? So let's try to have this following example. So for example, in this case here, we have a rectangle RWS or WRST or RSTW, which we also have the intersection here of some of the perpendicular, or it's point Z, the letter C. So it's asking us to find the measurement of the two diagonals. Now find RZ and SW. So, sorry, let's try to change the find. Oh yeah, that's too thick. For a moment, too thick. This one is a bit but big maybe. Yes. Right. So as I was saying, we are asked to find RZ. Find RZ and SW. This is only for this figure, huh? So let's try. So first things first is for you to determine the theorems that can be applied in this case. So note that there are really necessary theorems na we can also apply properties of parallelograms, especially finding lengths. But in this case, we can also use some theorem for the rectangle. So if you still remember, one theorem for a rectangle is that the diagonals of a rectangle are congruent. Remember, so we can just easily say that. If the RT is is equal to SW, but the given is not directly RT, rather it's RZ. So how do you get the value or the representation for RT? No, we can say that RT is equal to SW, but in the given, it's not directly given, it's RZ. Take note, right? Take note that one of the properties of a parallelogram is that the intersection of the diagonals of a parallelogram bisect each other. So that means RZ is equal to ZT, right? So that would also mean that RT can be represented as twice of RZ, right? Diba kay RT, RZ, then another T, equal naman isang TZ o RZ, right? So we can say that RT is equal to 2RZ. Now, in that case, we can rewrite the first equation into this 2RZ equal to SW, right? We change the color of the pen. So by substitution, you can also write beside the theorems for that. I'm just going to read it. Substitution, we can just say that 2 times 2x plus 5, was that correct? Equal to SW. What was SW again? 5x minus 20. All right. And then we do this distribution property, which is now 4x is 10 equal to 5x minus 20. Then we group all the terms containing x. In this case, since 5x is greater than 4x, I am just going to stay with the positive now. 5x minus 4x. So, and then that becomes 30 equal to x. So I can just have automatic value of x. So here, we can say that for RZ is equal to 2x plus 5, right? 2x plus 5 again, yeah. So RZ, we can say that RZ is equal to 30, 2 times 30 plus 5, which is also 65, right? As for SW and for RT, which is 2 times RZ, so 2 times 65 is 130, right? RT is 130. But how about SW? SW is, how much was it again? 5x minus 20. So 5x minus 20. Okay. Yeah. 5x minus 20. So when I substitute the value of x, which is the value of x again, 30. 30 minus 20 is 150. Wait, yeah. That is 130. Right? So units. So SW is 130, and which is the same with RT as well, diba? Since RT and W are diagonals, we check these two are equal, right? And also when we double RZ, we get 130. So yeah, I think that suffices, right? So how about another question? For example, is let's say this angle here is 60. Oh wait, let's say that's 30. Let's say this is 30 degrees on the side here. What do you think is the degree measure of RSZ, so this angle? So if that's the case, angle S is equal to 30 degrees. What do you think is the degree measure of angle RSZ? So this inside here, RSZ. So remember that rectangles, the angles, all angles of a rectangle measures 90 degrees, right? So in this case, this one is 30. So how do we get the RSZ? By subtracting it from, by subtracting angle S from 90. So 90 minus 90 degrees minus 30 degrees to get 60 degrees, right? So that's only for this case. Sure. How about that one that diagonals bisect the angles? Well, the opposite angles. Well, that's not for this shape. For a different shape. So that's why we're going to proceed to this one, the rhombus. So let me delete this part here. That's one for the rhombus. For the rhombus, for example, in this case, we to apply the one that you almost applied in here. So it's a different case, huh? Different shape, different cases, but at some point their times not they're equal and so. So, for example, you're asked to find the degree measure of angle 1, in this case, this figure. By the way, when you put degree measure M before the angle symbol, it's not necessary anymore to write degrees. Okay? So, for example, in this case, angle 1, rotating is the degree measure of angle 1. So remember that one theorem of rhombus it states that diagonals of a rhombus are perpendicular to each other. So if that's the case, angle 1 measures, when you say perpendicular, it forms 90 degrees, right? So if that's the case, angle 1 is 90. If it says just angle 1, you can write 90 degrees. But if it says degree measure of angle 1, okay. How about the degree measure of angle 2? Okay, what do you think is the degree measure of angle 2? So, what do you think? What do you think? So for degree measure of angle 2, degree measure of angle 2. So how do you get the degree measure for angle 2? Well, that's a separate case naman, no? So, how do we get that? Let me think. So if this remember that again, remember that in one of the theorems of the rhombus says that the diagonals of a rhombus bisects the vertex angles, no, or the vertex. That means if 70, what do you think here? That's also 70, right? So if it means bisect, it divides it into 2. So if this is 70, it follows that this part here also is 70. So if that's the case, if this is 70, 70, so 140, right? So, and if you apply, okay, if you apply another property of parallelogram, which states that consecutive angles, okay, consecutive angles of parallelograms are supplementary. If this is 140, what's the supplement? What are we going to add with 140 to make it 180? It's 40, right? So if that's the case, this one here, the whole thing here is 40. You divide that by 2, therefore degree measure of angle 2 is 20, right? Now, how about degree measure of angle 3? Well, degree measure of angle 3, it follows naman since they are just opposite angles man sila, diba? So if this is 40 earlier, this follows that this one is also 40. E divided by 2, that's also 20. What about angle 4? Well, for angle 4, you just automatically say that it's also 70, okay? Angle 4, sorry. So it's also 70. How come? Remember that these two are opposite angles, okay? When you say opposite angles of parallelograms, they're equal. So if this is 140, this is also 140 here. Okay, divide by 2, that's also 70. Okay? So that's only for the angles of one. Applying also with the perpendicularity of this one, maybe we can apply Pythagorean theorems at some point later on. Right? So let's proceed to the square. Square, when you say square, let's say this one is a square. You have to find this angle. Let's say angle 1, angle 2. Well, all the rest of the angles that will be like crossed by the two diagonals, they're all equals. For example, let's try to name them. This one here is angle. All the angles that were like split, no? The four angles that were split by the two diagonals are all equal, which means that angle 1 and angle 2 are just equal, no? So it means that 45 is equal to 45. So what about the measurement? Let's say, for example, this one is 2 units. So let's name this. Let me delete that one. So this is also a theorem. Remember the last one? I've included in the module, so you can just read it. But the example is not there. By the way, the proof for the two remaining theorems, I will not include it in this video because it will take some time. It's almost 1 a.m. So I'm just going to give you examples. I've already given you the 3 examples for 3 figures. So let me continue with the measurements for this instance. So if, for example, you have an diagonal here, let's just imagine. Now, let's say this one is named A, B, D, and the intersection here is E. So if this is let's say 2, if AE is 2, what is DB? Okay. What is DB? It also follows that DB is 4. How come? If DB is 4, if AE is 2, and that follows that AC, it implies that AC is equal to 4. And remember that the diagonals of a square are just equal, so it follows that DB is also equal to 4. Okay? Same way, you just have to divide everything by 2 if you're going to get that EB and ED, divide 4 by 2 lang, and so on. Okay? I think I'll just have to stop there, and hopefully you'll be able to answer the questions from the activity. I've posted some examples for every solution, problem solving, so you can just refer to that. God bless everyone.